Section 4.4, the logistic equation. The logistic equation is something that's designed to simulate population growth. Well, we've already seen a simulation of population growth where we use the exponential function. Okay, like this. An exponential function is something that starts slow and then start growing fast. And that is a pretty good simulation for things that are in good conditions and then in the beginning of the growth where things are great and there's more than enough food for everybody and no predators and all that stuff, so the thing is just going to take off. However, that's not practical because the exponential simulation means that it's just going to go and take off and doesn't look back, which is not true in real life. In real life, of course, the population grows to a certain point, then they run out of food or run out of something, and then they're just gonna to settle. Okay, so then we need a better simulation for the population growth, and to look at that, or any problem that looks like the population growth. Now, to look at that, we have certain definitions. Let's look at the next page. First, the carrying capacity means that how much the population can grow as the maximum. The maximum population of the organism can sustain indefinitely. In other words, is the formula when t approaches infinity, that's the more it's going to be. You know, it approaches an asymptote because, as we know in real life, nothing grows infinitely. It doesn't work that way. So we are going to come up with a different plan of representing population, and the different plan looks like the previous one with some conditions attached. So the new formula is called the derivative of the population with respect to time equals the rate of the growth. Okay, which that's the original formula from which we derive the exponential growth. And then, but we're going to write down a condition, a restricting condition in there, which is population divided by the carrying capacity. K here stands for population, and K stands for the carrying capacity, P stands for the population, and R is just the rate of growth. Now, at this point, you notice that as the rate of change in the beginning, when P is very small, then it's just a similar or identical to the original formula. But as P increases, then the original growth got tempered by this subtraction. And as P approached K, then this number is the rate of change approached 0. That is, the population approached some kind of a constant. So that's how this formula works. Now that we got the formula out, we have to solve the formula because the formula is in the form of differential equation. So let's flip over a couple of pages. Let's skip the example 4.14. And first, let's solve this formula, okay? Then we'll stare at the 4.14 and use that as an example to see how the formula works. So flipping a couple of pages further, let's look at page 399. So on page 399, we are going to solve this equation by the trick that we already know, separation of variables. Now, this equation is autonomous, which means there's only everything is in terms of our main variable. It doesn't even have t on the other side, which means so then we're going to pull the trick of the solving autonomous, well, just separated variables. There's nothing even much to separate, which means we stick every single thing on this side. There's dp, and then stick everything down here, okay? Because that's rp minus r over k p. Now keep in mind what this thing is. This is we'll integrate this thing, okay? Stick the integral sign there. Now keep in mind that of all this stuff, only p is the independent variable. Everything else is just numbers, okay? We don't know what they are right now, but we don't care. They're just numbers. They just come in for the ride. We don't do anything with them. And then this side, we have dt, all right? So now we are going to do a bit of this is a fraction, right? let's see, give me a second. RP minus, oh, there's a p squared, sorry. There's a p squared here. So this is a fraction that we're going to need to break it, okay? So then let's break it. And how are we going to break this fraction? So first, we're going to clean up the fraction a little bit so we can see it better. There's an r down here, so we'll move r to the other side. There's a k on the bottom, so we'll flip it back on top. So then our integral becomes, so then becomes k, okay? And then dp, and then there's an r that r is gone because we'll put it on this side, r dt. And then we have p minus kp, so k will come over here, and minus p, which is a better equation. This is on the next page. Okay, I forgot the p squared again, so let's add that in, which is okay, but still, but how do you break that into fractions? That might be kind of a lot of work. So let's use the fraction generator. What is this thing called? Partial fractions calculator. The problem, however, is the partial fractions calculator is not going to let you put in variables, right? I mean, the k it has to be a number. So here's what I did. I plugged in some random number into the partial fraction. See, a prime number such as 11, and that looks identical to this. Now the k on top doesn't matter. We can just take it out. The question is, what does the bottom become? As you can see, if k was 11, okay, then this particular pattern shows up. Can you see it? That is, oh, there it is. Yeah, it's having a hard time focusing. Okay. Let me adjust the lighting. So anyway, so then as you can see, if you use the partial fractions calculator, it has maybe I turn it this way. Okay, then the lighting might be slightly better. Yeah. Anyway, so as you can see, there's a pattern that evolves. So I tried a couple more numbers and quickly come up with, you can quickly come up with this as the result, which is the pattern shows that this particular fraction will turn into this, okay? It becomes 1 over p with k on the outside. It becomes 1 over p plus 1 over k plus k minus p. And then that we have dp. And then I multiply, I put it together in the common denominator to make sure that this actually works. Actually, I think the k might need to be, no, there is no k. What is that? Let me, yeah, actually there is no k here. My point is that if you can still use the partial fractions calculator by substituting some numbers that will help you break up the fraction without working too hard. Anyway, so once we break up the fraction, which is how you solve this kind of integration, we have then we have something that's readily integrable. Okay, this is r is still here, dt, and then you integrate this thing by you get the natural log, of course. So we have natural log of p minus natural log of p in absolute value. Okay, natural log of let's see, it should be, this is a plus, so this is a plus, and then that becomes a minus because we have natural log of k minus p. And because of the minus, when you take the derivative, there will be an extra minus, so that take care of, that becomes, that makes this thing minus instead. That's just a bit of a detail. And then equals RT plus constant. All right, and from this point on, we have, so from this point on, we're done with integration and calculus, and now we plunge into algebra again. How do you solve this algebraic equation? Now in algebra, then we will actually, please perform this part of the proof all the way to the end of the solution to do the algebra part. What you do is then the subtraction in natural log becomes division, and then once you get everything under one natural log, okay, then the whole thing just you slap an E on there, and then the answer will come right out like this. But actually the answer doesn't come out right away. So the first part is okay, I guess. But then you have, so you have P over K minus P, then you have to solve for that, which isn't that much harder, right? That's basic algebra. Once you get that, you have P on top and the bottom of the fraction, then you yank it out by multiplying stuff and moving stuff around. Now focus, remember, P is the only variable here. Everything else is just some number. And then eventually you will come up with first yet a different constant, C1, and then you come up with some kind of a solution as the bottom shows. And that should, and of course, what is C1 eventually? Well, eventually, if you plug in the initial conditions for this differential equation, you get, if you get some conditions such as P at 0, the population at 0 is equal to some number, right? And then it's equal to P0, exactly. So then with that, you can quickly plug it in and calculate what is the constant exactly. And then but that's not all. Eventually, however, if you get the formula for P, after you calculate what C1 is, you can plug all that back in if you want. I don't know if that's necessary. Yeah, go ahead and do that. There's a bit more algebra, especially fractions, but if you get through all that stuff, then you look at the next page. Then eventually you get to the complete formula of this thing. Okay, you did the integration, and then the whole bunch of fractions and stuff, and everything cleans up pretty good to become P of t equals to that. That's the solution to the logistic differential equation. Okay, so the solution is already done. So please do this part as part of your homework. That is basically starting from page 399, starting from this equation and work your way all the way down to that answer, which is a small amount of integration and a huge amount of algebra. So please do that, because to work in algebra with that many symbols in there is a good practice, so that you don't. I need to stop touching my microphone. And so that way you can get used to doing this type of thing. And that is actually the whole point of this section, is that you know how to do algebra. And so now that we're done talking, now that we're done proving the integration, how to solve the differential equation, now let's go back to the previous example, where you have a deer situation. Now, in the book, the example 4.14 spans several pages, because instead of getting to the answer and plugging in the numbers, they started here and did each step with the example's numbers, which are huge. Like, for example, the deer population, the carrying capacity, it happens to be 1,072,764, which they plugged it into the K every single step. I'm not sure why. Maybe the book is trying to get you to get used to, I don't know, facing real world problems. But even in real world problems, you're not going to do this. You're going to, go to the formula and plug all the real world numbers right into your formula. So, but anyway, please do that problem and look through all the typing your book did. They typed 1,072,764 how many times? I don't know, maybe 30 or something. It shows up a lot, which I find that very comical. Anyway, so please look through that. But in reality, we already found the solution. All you have to do is plug in the deer population okay, the growth rate, the carrying capacity, and where's the answer? Yeah, plug it into the answer, the solution, which is right here. Okay, here's your solution, and you just plug in and the initial population, right? We plug in all the symbols properly, and out pops your answer. There's no need to write 1,000,000 50 times, however many times your book typed it. But anyway, so once you see the answer, then the solution actually has a graph. Now, look at the solution graph on page 402, which shows you what the growth is, how the growth is being predicted. See, the growth in this case is more. The graph is more reasonable because you start at P0, which is 900, and then the graph goes up, and then eventually tapers off at 1,000,000 something. That same number that your book likes to type so much. That's all there is to it. And that, of course, is far better than the exponential growth, which just starts sprouting and then goes to, takes off without bounds, and you have a trillion deer in your county, which is not going to happen. Okay, and so this new simulation is a much better expectation. So having said that, there are certain other details that you can calculate. For example, from the solution problem, you can calculate things such as how long does it take for the deer to reach a certain population. And for this equation, like for example, let's see. Let's say your deer's P0 is at 500,000 deer. How long does it take to reach, say, 900,000? Then you write down 900,000 on this side, right? And then the other side you solve for t, where everything else are just numbers, constant numbers. And that is a straightforward algebra problem. Yeah, and that's about all there is to this section. This section talks about one math problem with extremely simple integration. All the rest of it is just algebra with big numbers. Okay, so then, but please do this proof. Okay, that's the only thing this section is about. So please do this proof, this problem yourself to make sure you know how to do this integration from here all the way to wherever the book wants you to go. Having said that, let's do, so that's that. So let's do homework problems. For homework, which is on page 405, please do problems 175, 194, and 197. And out of those, one of them is actually interesting that I want to talk about. So after you finish your homework, come back, and then we'll talk about the one problem. I think it's 197. Now, problem 175 is a matter of you want to find out what the number of years. Now, it's a quick algebraic manipulation, except that you're going to have to deal with a lot of variables. So the one way I suggest that you do is do something like this over here. You let P0k equal to the letter A, k minus P0 as letter B, and P0 equal to C, and rewrite the equation, make it a lot simpler, and then come up with the answer, which is right here, and then plug everything back in, and then you calculate what it is. It's much faster. This is directly opposite of what the book wants to do, which is to have you write in all the big long numbers right there in the middle of your proof, which I don't know why they want to do that, because I thought algebra, the principle of algebra is you always use a simple symbol to represent a big, long, complicated formula or a string of stuff so that you don't have to write so much. But I don't know. But yeah, so in any case, we're going to do problems the easy way, okay? We'll let the book do stuff the hard way because it's a free country. You can do stuff hard way if you want. So that's problem 175. And next, let's look at problem 196. What is called? The Gomez equation. Now in problem 196, you're supposed to solve the Gomez equation. And Gomper's, excuse me. And what is that? That is, if you look back at problem 194, then it tells you what it is this particularly interesting equation, okay, where P is inside the natural log. and so on. Now, okay, so there's the solution, and how we're going to solve this equation, the differential equation. So let's give it a try. Like I said, this is just about the only thing that's interesting in this entire section. Okay, we actually need to solve something that means something. So let's write down the equation here. Okay, the Gomperz equation says that you have alpha on some number times p of t, which I replace it as y because we're used to doing y, so I want to continue doing it. But you can totally use p, of course, if you prefer. Now, anyways, I have alpha times y, and then and what else does it say? It's the natural log of k over y. Okay, where y equals the p of t. So y equals to p of t. I just want to change it so that everything looks simpler and neater. Having written down the equation, let's see how we're going to solve this thing. Okay, now being that y is on the bottom here of the denominator, that makes it harder. So, and that looks all confusing and weird. I wouldn't even know how to solve that. So first, let's make this easier by doing this. Alpha y natural log of k to the power minus 1, okay, and y to the power minus 1. That is, let's see, k to the power minus 1 to the power minus 1. And what I'm doing here is, right, and what that means is that I can take the minus 1 out of there, or maybe that looks a bit confusing. What I mean is this. The negative 1 will be written outside, like this, see? Then this one, if you multiply back in, that's k, and that's y to the power minus 1. And the reason I want to write it out there is so that I can put it in front. So then it becomes minus alpha y natural log of k minus 1y. And then that way, at least my y is not in the denominator, which might make the integration easier to do. Now, having done that, let's integrate. Okay, the y prime, which is dy by dt. Okay, y prime is just dy by dt. And we're going to do the separation of variables. There's nothing to separate because this is an autonomous equation. Therefore, we're going to have to integrate everything here goes on the bottom. Or maybe we'll put the minus and alpha on the other side. All right, so the minus and the alpha goes on the other side, dt. And then all the other heavy lifting goes on this side. Over, okay, that is minus alpha, which is, well, anyway, y natural log k inverse k to the power minus 1 of y. All right, so far so good. Now, in that case, where am I? Okay. And then that looks, slightly better, but how are we going to integrate this? There's a natural log of y and all that stuff, which looks a bit hard at first until we realize that we just have to do something called, let's see, did I write my alpha correctly? No, I think alpha is multiplying here, because alpha is at the bottom here, so it should be multiplying, right? So alpha is multiplying, so let's not get the algebra wrong. Is everything right? I think so. Okay, let's move along. And then, so we're going to at this point, we're going to do a simple substitution, which will solve this problem. U equal to k inverse y. And then, is that right? Yep. So then everything's good, because then we're just integrating, what is du? Du equals to, sorry, there's minus 1 here, right? Here is, no, wait a second. Let me make sure I didn't mess up. See, I knew I got something wrong. Y is not minus. There's no minus here. U is not equal to k inverse y. It's natural log of k inverse y. U equals ln of k See? That's what I have it written down right here. See? And anyway, so then we're going to do that. That way du equals to the derivative of this thing, which is equal to 1 over k negative 1 y, and then multiply by this thing, which is another k minus 1 y, the y. And then these things conveniently disappear. I always love it when stuff conveniently disappear. So then the entire equation, when we substitute back in, becomes this du over u. That's it. Which equals to minus the integral of minus alpha. And alpha is just a symbol. I mean, just a number. We don't care what it is. It just tag along like a constant. And then we're going to integrate this thing, okay? And we all know how to integrate that. And so that at this point, the calculus part is over, and we're going to do the rest is algebra. And then, of course, when you integrate it, then you get this solution that I have written down before, right? And then how do you, the rest is just what is that? Okay, the next page. So the next page is all algebra. Okay, let's see you. So please finish the rest. See, actually, you don't need to finish. This is homework. So anyway, so the rest of algebra, as you can see what I did, you do the same thing. It's the natural log, of course. And then you integrate it, and you have some c's. The c's, sometimes you might worry about when you integrate that the c is positive and negative because of the absolute value sign. As it turns out, you really don't have to think too much about that. Yeah, sort of. Yeah, it's like every time the absolute value shows up, we end up sort of ignoring it. So bear in mind there's a positive and negative situation, but at the same time, it's just a constant. And we don't care what constant it is, so it doesn't really affect that much. So we're going to do that, and then eventually we come up with the exact equation of this thing. And this equation, there's no answer at the back of the book, but I did Google it, and this is the solution to the Openstax problem. I confirmed it. Okay, and then of course after that you figure out you plug in P0 or something, and then come up with some kind of answer, and that answer is the same as the back of the book, so it is correct. And with that, we have come to the end of this section, which is actually doing basically one problem, except for the Openstax problem, which is slightly harder. As you can notice that both these sections, we've been doing a ton of algebra and very small amount of calculus. So if you have trouble with the algebra, please brush up on your algebra. And more importantly, do not be threatened by big numbers or a bunch of symbols with subscripts in, like C0, C1, e to the power alpha, and then you P0 minus k and da da da. Do not let that confuse you. All those are just numbers, okay? You can punch them out in the calculator in a jiffy. We don't care. The only thing we care about is the integration, which happens to be one step. Look at this. And this one, 2 steps, okay? You have to substitute u as the natural log, but otherwise, straightforward integration. So this is this section just shows you how big numbers can get in real life problems, but at the same time is as far as calculus is concerned, we're not really doing any heavy lifting here.